Okay, this is a continued recording of the Chapter 1 review. I want to go over these last few problems here. I cut it off because the other one was kind of long. Understand that the original test was a 2-day test, and the take-home test is kind of a 2-day process. And the original test would have cut off after problem number 11, and the second part started with problem number 12. But I'm just doing the second part of the review starting with this problem right here, problem number 16. Okay? This will be on the test because I need to make sure that students know how to reduce inverse sine, inverse cosine problems to the correct quadrant. In all likelihood, they're both going to be negative because that's where the problem usually comes in. So read the directions. Give the measures of the angles in radians and degrees. I probably shouldn't have asked for degrees, but here it is. Draw the terminal side in the correct quadrant. Label the sides of the triangle correctly. Here's the key. This notation right here means one answer, and the answer has to be written the correct way. There's only one way to write it. All students take calculus. The sign is positive in the first and the second, so it's negative in the third and the fourth. But which one am I going to pick to draw my triangle? It's going to be the fourth quadrant when it's the arc sine of a negative number. It's always a fourth quadrant answer. The opposite is -1. The hypotenuse is 2. 2 squared is 4. -1 squared is 1. 4 minus 1 is 3. But we should recognize it's the square root of 3. And it's positive because it's going to the right. Across from a 1 is a 30-degree reference angle. If you say the answer is 330 degrees, it's incorrect. If you say it's 11 pi over 6, incorrect. It has to be a number between -90 and +90 degrees, or negative pi over 2 and positive pi over 2. The only way to write this answer in degrees is -30 degrees. That's the only way we can write it. 30 degrees is the same as pi over 6, so that's negative pi over 6 radians. The key is, do you know how to restrict it to the one answer that applies on these problems? Same here. Inverse cosine. Remember, if it's an inverse sine on a positive number, it's always a first quadrant answer. So it's always a number between 0 and 90 degrees or 0 and pi over 2 radians. It's the inverse trig of these negative values that create issues. Remember that the inverse sine, inverse tangent of a negative number is always... Okay, so when we're looking at problem B here, and again remembering, for arc sine is negative pi over 2 to positive pi over 2. Arc tangent is negative pi over 2 to positive pi over 2. But arc cosine is 0 to pi. And you have to know those range of acceptable answers. It's the range. One thing that I did give you is a problem in which you have to rationalize the numerator. So I have to multiply this fraction by the square root of 2 over the square root of 2. Same thing as multiplying by 1. And in doing so, square root of 2 times square root of 2 is 2. I'll make it negative. The bottom is 2 square root of 2. And look what happens. The 2's cancel. I get -1 over the square root of 2. So we have to recognize when we see the square root of 2 over 2, it's the same thing as 1 over the square root of 2. We just rationalize the numerator instead of rationalizing the denominator. But if we draw a picture of this, we're not going to recognize the special right triangle. If we draw a picture of this, we should. Okay? You should recognize it from here. But all students take calculus. The cosine is positive in the first and the fourth, therefore it's negative in the second and the third. But I have to know it's the second quadrant answer that I'm in search of when it uses this notation. One answer. This is adjacent over hypotenuse. That's -1 over the square root of 2. 1 squared, so that's 1. Be careful, across from the 1 and a 1 square root of 2, that's a 45 degree. When the legs are the same size, it has to be an isosceles right triangle. It has to be a 45, 45, 90. If my reference angle is 45 degrees, when I come this direction, it's 180 minus 45 degrees is 135 degrees. Or 3 45-degree angles. 1, 2, 3 45-degree angles. That's 3 pi over 4s. Remember, the range of acceptable answers for inverse cosine is between 0 and pi. Unlike here, the range of acceptable answers for arc sine is from negative pi over 2 to positive pi over 2. We have to know the range. They're not going to give it to you on that. We have to know it. It's going to be on the test, and we need to make sure we can identify that one angle. We just write it in terms of degrees and radians, but it's the same angle. Okay? Okay. Problem number 7. Solve for y, simplify completely. So this is really, I think, the same problem as that maybe we talked about in the notes, or it's very similar. If I want to solve for y, I have to add this term away from it. The only term that involves y is this first natural log of y plus 3 term. So I'll add the natural log of 5. It's just a number. I'll add it to both sides of this equation, which creates a positive natural log of 5 on this side. I have 2 natural logs. We have a property for logarithms that says if I am adding natural logs, I can make it 1 natural log and multiply the arguments. X times 5 is 5x. We always write the coefficient first. You can put parentheses around it if you want, but it's fine. Okay? And I want to smash those together before I take e raised to both sides. Why do I take e raised to both sides? That's the only way I can dig out this y. I have to dig it out. The inverse operation, the inverse function of a natural log is e raised to. So if I take e raised to this side, I have y plus 3 left. If I take e raised to the right side, it looks like this. This next step is the most critical step, and you must show this step right here. Okay, I have to see this on your test or you will miss a point for not showing it, even if you have the right answer. We have an Algebra 1 property for exponents that says if you multiply like bases, you may add the exponents and write one base. That same rule works in reverse order. When I'm multiplying like bases, I can add the exponents. That means if I'm adding exponents, I can treat it as a multiplication of like bases. If I gave you this and said, write this with one base and one exponent, you would all say, oh, I'm multiplying like bases, I'll add the exponents. It's the same property in reverse. Why do we want to do this? Because we never want to leave a natural log in the exponent of e. These are inverse operations. But before I can apply this inverse property, I have to write it this way. So that now this here, e to a natural log, undoes each other. And I get 5x. And here's a y plus 3. So just so that you can see every step before I subtract the 3 over, I think it's important that you know the order of, this is a factor, e to the x squared. 5 is a factor, x is a factor. A numerical factor should always be first. Any polynomial factor should be second. Then any trig factor, any logarithmic factor, any exponential factor. The more complicated the function, have that be the last factor. Any numerical definitely out front. Subtract the 3 to the other side. And here is this equation. Solved for y. No more natural log at all. We're able to eliminate all the natural logs and write it like this. Okay? This is the way it will need to be simplified. This step right here is the Algebra 1 step in reverse, is the most critical step in this process. Okay? Problem number 18. The difference between the arc sine, arc cosine problem and this problem is that now they give us this range of answers. Actually, the domain we're solving for t. Okay? They tell us the interval for which t works. And it's from 0 to 2 pi, so any revolution counts. Well, there are 2 times that the sine equals a negative number. All students take calculus. The sine is positive in the first and the second, therefore the sine is negative in the third and the fourth. Opposite over hypotenuse. SOHCAHTOA. Sine is opposite over hypotenuse. The opposite is -1, the hypotenuse is 2. Opposite is -1, the hypotenuse is 2. Either use the Pythagorean theorem or remember that this is 1 square root of 3, 2. Notice that I labeled these sides with negatives. I want to indicate backwards is a negative, down is a negative. We can see why the sine is positive in these quadrants, because the opposite's always going to be negative, the hypotenuse is always going to be positive. Okay? Where the sine would be positive up here because the opposite would be positive 1. Let's just find the angles in degrees first. Remember, across from 1 is a 30-degree angle if it's a 1 square root of 3, 2 right triangle. You have to have it memorized. A 1 square root of 2 is a 45, 45, 90. The hypotenuse is the square root of 2. So this is a 30-degree angle. 180 plus 30 is 210 degrees. 330 minus 30, I'll say this again, 360 degrees minus 30 is 330 degrees. 210 degrees, that's 7 times 30 is 210. I need 7 30-degree angles, 7 pi over 6s. 330 degrees. 330 degrees is 11 30-degree angles. So I need 11 pi over 6s. That's it. That's the easiest way to convert. It has to be in radians. Both of these angles are between 0 and 2 pi. Problem number 19. Solve the following equation. Draw a reference triangle in the correct quadrant or draw the unit circle. Well, this is not a unit circle, it's a reference. I'm going to do this. Remember, u equals 2t. And I'm going to rewrite the original equation as the cosine of u equals negative square root of 3 over 2. What's making this problem complicated? The 2 in front of the t. Okay, let's simplify it. I can draw pictures of this angle, u. All students take calculus. The cosine is positive in the first and the fourth, therefore it's negative in the second and the third. SOHCAHTOA. Cosine is adjacent over hypotenuse. If this is the square root of 3 and that's 2, that makes this a 1. This is 1. I make it negative because it's going down. Notice the cosine in both these is negative square root of 3 over 2, so I do get negative. That's why we always want to label the side as a positive side or a negative side. Across from 1 is a 30-degree angle. 30-degree angle. So this first one here is 150 degrees. The one in the third quadrant is 210 degrees, 180 plus 30. But we have to convert them. 150 degrees is 5 30-degree angles. It's 5 pi over 6, because pi over 6 is a 30-degree angle. 210 degrees is 7 pi over 6. Okay? Those are values of u. Now here's where we have to be careful, because this 2 actually does 2 things. That tells me how many rotations that I have to take. So I have to add another 2 pi to this and another 2 pi to this to solve for u. Because this 2 tells me I need to look at 2 rotations. If I add 2 pi, Adding 2 pi is the same as adding 12 pi over 6. We have to be able to add fractions. 12 pi over 6 plus 5 pi over 6 is 17 pi over 6. Okay? 7 pi over 6 plus 2 pi is adding 12 pi over 6. 12 plus 7 is 19 pi over 6. But these are my values for u, not x. This is what u equals. I solve for u because I did this replacement. But look, now if I go back and solve for t, if I just multiply both sides by 1/2, there's t. So I just have to take every one of my u values and multiply it by 1/2 in order to get my t values. If I multiply by 1/2, I get 5 pi over 12. I get, multiply this by 1/2, 7 pi over 12. 17 pi over 12. And 19 pi over 12. Those are my 4 solutions. Okay? Notice, are all of my answers between 0 and 2 pi? Well, 2 pi is the same as 24 pi over 12. 24 divided by 2 is 2 pi. 24 pi over 12. Yeah, 19 pi over 12 is less than 24 pi over 12. It works. But if I did another revolution, it would be too big. Let's do another one of these. I like to do this. U equals pi over 2 times t. Therefore, I can rewrite this as the sine of u equals 0. If it equals 0, it's always a quadrantal angle. If we're looking at an undefined situation, it's always a quadrantal angle. If we're looking at a trig function equaling 1 or -1, it's usually a quadrantal angle unless it's the tangent of u equals 1 or -1. Then that's a 45, 45, 90. So draw yourself the unit circle. Label the 4 points. This is the point 1, 0. This is the point 0, 1. This is the point back 1, up or down 0. This is the point left or right 0, down 1. I want to know when the sine of an angle equals 0. For a quadrantal, the sine of a quadrantal angle is the y coordinate. So this is essentially saying, when does the y coordinate equal 0? The y coordinate's 1 here. It's -1. Here's where it equals 0. Here and here. So that means u is 0. U is pi. Now, what makes this hard is this is between 0 and 12. So I don't know how many of these I'm going to need. But I could go 2 pi, 3 pi, 4 pi, 5 pi, 3 pi, 4 pi, 5 pi, ... I don't know how many I'm going to need. And I don't have to write them all out. Let's come back and look at this. To solve for t, I'm going to take each u and multiply it by 2 over pi. So each one of these, the pi is going to cancel out of each one of these when I solve for x. Right? If I multiply this by 2 over pi, the 2 is going to cancel. So 0 times 2 over pi is still 0. But multiply this by 2 over pi. Pi cancels, it's 2. Multiply this by 2 over pi. Pi cancels, 2 times 2 is 4. Multiply this by 2 over pi. Pi cancels, it's 6. Multiply this by 2 over pi. The pi cancels, it's 8. I can see the pattern, it's 10. 12 is in this interval. So I include 12. I go up until the number exceeds the right endpoint of my interval. That's it. That's how you figure them out. Last few problems. We didn't see much of this, if at all. I don't know how much of this I'll actually put on the actual test, but I definitely want you to practice it on the review, and I want you to practice it on the take-home test. This is a concept we will do frequently once we get into derivatives. The big separator is this subtraction sign right here. I'll actually put it in blue so you can see it. If I want to factor, are there common factors on both sides of that subtraction sign? Yeah, x minus 2. That's a common factor. So I can pull an x minus 2 out front. How many can I pull out front? It's always the smaller of the two exponents. Negative 1/2 is smaller than 1/2. So that comes out front. If I do that, what is going to be left? Well, I have a 2 left here. But how many x minus 2's are going to be left? I always take the larger exponent and subtract the smaller to figure out how many are left. 1/2 minus negative 1/2 is 1/2 plus 1/2, or 1. And when you're taking derivatives, it's always going to be 1. When I pull this out front, that's already out front, I still have an x left. Now I can simplify this down. X minus 2 to the negative 1/2, 2x minus 2 minus x, turns out to be this. This part right here, 2x minus x, is x minus 2. Okay, oh, when I distribute the 2 here, that should have been a 4. Sorry about that. Okay, should be a 4. So on top, 2x minus x is x minus 4. To make this exponent positive, I have to drop the base down to the denominator so I can make this exponent positive. The directions say in correct radical form. A fractional exponent is not written in radical form. So anything raised to the 1/2 power is a square root. That's why we get this. We want to write it this way because I want to know when this function equals 0. This function equals 0 at x equals 4. I want to know when is this function undefined. It's undefined when x equals 2. We're going to do this a ton in chapters 3 and 4. Okay? Remember our rule for factorization. Factor out the smaller of the two exponents, take the larger exponent, and subtract the smaller. 1/2 minus negative 1/2 is 1/2 plus 1/2, or 1. Problem 22, we did do problems like problem 22. I just threw one on at the end. Add 3 to both sides. E to the 3x equals 14. How do I solve for a variable that's in the exponent of e? Well, the inverse of e is natural log. So I take the natural log of both sides. Why? Because this drops down. 3x times the natural log of e. Or you can say natural log undoes e, and you're just left with 3x. But the natural log of e is always 1. We should know that as well, that the natural log of e is always 1. If the base is e, what does the exponent have to be to produce an e? 1. 3x times 1 is 3x. And divide both sides by 3. This will be a non-calculator test, so we would just leave our answer in its analytical form. Okay? There's that one, there's that one. 2 left. This problem is all about knowing this. 5 times 0 squared is 0. 2 times 0 is 0. 0 minus 3, there's a negative 3. 3 times 0 is 0. Minus 0 cubed is 0 times 6 is 0. Minus 2 times 0 is 0. Plus 2. This is the cosine of 0 squared is 0. I'm giving you this problem because I cannot tell you how much on the AP test you're going to have to evaluate e at 0 and cosine at 0. Because students want to make those values just 0, and they are not. Here I get negative 3, but e to the 0 is 1. Anything raised to a power of 0 is 1, not 0. Here's 2. Same thing here. The cosine of 0. The cosine of 0. I have to use the unit circle. That's the 0.10. That's the angle of 0. The cosine of 0 is 1. It's the x-coordinate at 0. It's 1. And they try to get you on this all the time. We have to know that the cosine of 0 is 1 and that e to the 0 is 1. This is -3 minus 2, which is -5. Done. Last problem. I'm not sure if this one's going to be on the test because of the abstract nature of it. But this is another problem that we're going to do frequently in chapters 7 and 8. Okay? So essentially this problem says, when you plug 0 in, you should get 5 out. If I do that, and here's the problem. If I plug in 0 for x, I get out 5. 3 times 0 plus c. This is a c here. It stands for arbitrary constant. Okay? So that's a c. Well, 3 times 0 is 0. This is e to the c. How do I solve for c? Undo the natural log. Or undo the e raised to, take the natural log of both sides. The natural log of e to the c is the natural log of 5. But if I plug this back in here, we have a natural log in the exponent. We cannot have a natural log in the exponent. So this is that same problem. I'm adding exponents. I can rewrite it as a multiplication of like bases. If I gave you this and said, write this same expression only using one e and one exponent, you would write it like that. You'd say, oh, I'm multiplying like bases, so I'll add the exponents. It's just the same thing in reverse. E undoes the natural log. We get a 5. If it's a factor of 5, we always want to write that out front. And that's what we get. And we have to be able to write them this way. Okay? Now, there is a little shortcut to this. Let me show you this. Just real quick. I'll do it in pen. And this is how we're going to do this later on. We're going to apply the same rule I used here. This is the key step. But if I apply it right away to this, I could rewrite this as e to the 3x times e to the c, where c is some arbitrary constant. Well, e raised to an arbitrary constant is just an arbitrary constant. It's just a number. I just don't know what it is. How about we call it a instead? And we write it out front. It's a coefficient of this. Why is it nice to do it this way? Because now if I plug in this condition, if I plug in 0 for x, e to the 0 is 1, I just get a instead of equal to 5. And if I plug 5 back in for a, because that's the initial amount, I get to the answer much more quickly. I would actually prefer that you do it like this on your test, but you must show me this step and this step before the answer. 1, 2, then the answer. But if you do it this way, it's fine. It'll work out the same. But later on in chapter 7 and 8, we're going to do it this way. Okay? So that's a half hour. The first one was about an hour. I'm going to send these both out as you work through it, and hopefully you listen through these reviews. Okay? Checking out the solutions.